All right, we're working on section 6.6 right now, area between two curves. This is actually a pretty short section. It's important, but you'll find that once you know how to do one or two examples, they all kind of follow suit. So I have two examples for you, and then you can work on some homework after that for 6.6. So today we're going to find the area between two curves. So you already talked about how to find the area between the x-axis and a curve that lies above or below. Now we're going to talk about how to find the area between two different distinct function curves, like you would see in this graphic to the right. We're interested in finding the area below f of x and above g of x on the interval from a to b as shown. So basically just the area of this shaded region. Now, sometimes you'll be given bounds for a and b, and other times you're going to have to find them yourself, which is fine. And you know how to do that using algebra. We're going to look at this graph where f of x and g of f are continuous functions from a to b. And in this case, it is specified that f of x is greater than g of x. So this is really important because sometimes students tend to think that whatever the graph is labeled as, if it's labeled as f or it's labeled as g, f must always be the top one, g must always be the bottom one. But be careful with the labels. Your text actually and your homework are pretty good about not labeling them f and g. F is always going to be the greater function. So when you're seeing this notation, this means that f is the top function. And then g is the bottom function. I'm going to show you a second example where the top function changes. So it's one graph and then they intersect and then it's another graph. So we'll talk about that instance as well. So the area under f of x is just the integral from a to b, in this case, of f of x dx. And the area under g of x is the integral from b of g of x dx. Now, if I was trying to find the area between these two, the idea is that I want to take away this area that's under g. So the area under g of x is this piece. So right here, that's the area under g of x. The area under f contains this whole space between the curve f and the x-axis. So if I take away the area under the curve g, that's going to isolate just the area between the curves f and g. So the idea here is we can still use the integral from a to b, but now what I'm going to do is I'm going to take the difference of f and g dx. And remember that in this case, f is always going to be whatever function is on the top. So top function minus bottom function. Okay, and you can see why that would have to be. So let me give you an example of what this is going to look like in an exercise for you, the type of thing you'll be seeing on your homework. Find the area area bounded by the graphs of and we're going to have g of x equals 9 minus x squared and h of x is x plus 3. Okay. I always recommend that you do a quick sketch, whether that's by hand or in your graphing calculator. That is absolutely up to you, but I think it will be extremely helpful in figuring out which function is the top function and which one is the bottom function. And if you're not going to have a situation here where these change, like you're going to see in example 2, because we're just finding the area bounded by these two graphs. And maybe I spoke too soon. You're going to have to graph it to make sure that one function is always the top function and the other function is always the bottom function. And another thing you're going to have to do is figure out where these two intersect. Now, I'm going to go ahead and just do a quick sketch. So 9 minus x squared, if x is 0, g of x is 9. And then this is just your standard parabola. That's going to be 8. So that means this will be 4, 6, 2. So I'm going to bring my 2. This is 1. Oh, my scale is off. That's okay. If you do a really nice job sketching this, you will find that it's actually easier to even find these intersection points. Okay, don't forget your parabola exists on both sides. And then when x is 3, g of x is 0. We have this situation here. We have this parabola. This is g of x equals 9 minus x squared. And then the other graph is h of x is x plus 3. So y equals mx plus b, the slope is 1, the y-intercept is 3. So that means the y-intercept is here at 3. If the slope is 1, you're going to go up 1, right 1, up 1, right 1. And I'm guessing that this is where I'm going to have an intersection, but I don't know, because I did a not so great job scaling this, and it's just a quick sketch. I'm not looking at any graph paper here. This is what I think is going to happen. Okay. If x is -3, h of x is 0. So this will be the point at -3, 0. There's a point here at 3, 0. And then what we're trying to do is we're trying to find the area between the two graphs. And the area between the two graphs is going to be in here. So this is what we're trying to find right now. Okay, so in the example above, it's a little bit different in this general example because you were given bounds A and B. Basically, it was just like, okay, integrate from here to there. But this was a little bit different because you're not being told integrate from here to there. You're being asked to find the area between the two curves. So you're going to need to figure out what the values of A and B are. And you're going to do that by finding the intersection of these two. Now, again, if you did a really nice job sketching it, you should get the first one to be -3, since x is going to start at this intersection point at -3. Well, and it's going to work its way to the right until you get over to here. Now, again, if you did a really good job sketching this, that should be pretty clear to you where that value is. But that's not always going to be the case. And sometimes these values might not be integers. They might be fractions or even irrational numbers. So we're going to solve for these by solving the system of equations to find their intersection points. So basically, if you have g of x equals, you have a y equals, and if you have an h of x equals, you also have a y equals. So if I want to figure out what these two functions have the same value, I can just set them equal to each other. Set g of x equal to h of x to find the intersection x values. And then that's going to tell me my limits of integration. And then I'll know, okay, I'm going from here to there. I just need to make sure I'm covering the area of this region from left to right. So when I set these two equal to each other, I get 9 minus x squared equals x plus 3. And then we'll solve. Now, anytime I'm trying to solve a quadratic equation, and I know this is quadratic because I have an x squared term in it, I will get all terms to one side and get the equation set equal to 0. So I'm going to add the x squared and subtract the 9 from both sides. So this is going to become x squared plus x. So I still have this x here. And then when I subtract the 9, I'm going to get minus 6 equals 0. Now, I just decided I wanted all my terms on the left. That's a personal choice. You can have them on the right if you want. It does not matter. But the reason I did subtract x and subtract 3 is just because I like for the lead coefficient to be positive if I can help it. Now all I have to do is factor this and solve. It's easier to factor if lead coefficient is 1. So I'm looking for two numbers that multiply to -6 and add to +1. Whatever you do, don't choose. What do students always choose? They choose like -6 and 1, or what do they do? I don't know. Students always want to factor this wrong, and I don't remember how they do it. But anyway, it does not matter. The two numbers that multiply to give you -6 and add to give you +1 are going to be -2 and +3. And always check that. But these two multiply together. A negative times a positive will give you a negative. And when you add up -2 plus, you get +1. And then you end up with x equals 2 and x equals -3. These are the values of a and b. So the smaller one is going to be your a, your lower limit of integration, and the larger one will be your upper limit of integration. So remember, you're thinking about this as moving from left to right. Okay, so let's go ahead and set up our integral then. I have the limits of integration. That's probably the harder part of this. And I'm going to integrate this from -3 to 2. And what I'm going to do now is I'm going to take the top function minus the bottom. So try not to think about this as always being f and g. Remember, f just denotes the top function, g just denotes the bottom function. And in this case, g actually represents the top function. So don't think of g as being the bottom function. I'm taking the top function, which I know is 9 minus x squared. And I'm subtracting off the bottom function, which is this linear equation, this straight line, x plus 3. Now, it's really, really important that you remember here to include parentheses, because when you're subtracting off the bottom function, most of the time, you're subtracting off more than one term. If you're subtracting off more than one term, you need to make sure that this negative sign is getting distributed into the parentheses. This integration problem in and of itself is really super straightforward. It's just a 6.1 problem. We just need to make sure we can simplify it out and evaluate this correctly using the UTC. So let's rewrite it. I'm just going to write this in descending order. -x squared, and then it's minus x, and then it's 9 minus 3, which is 6. Now, if this looks familiar to you, if you've done this correctly, usually what happens is you either get this equation back, the one that you used to find the intersection points, or you'll get its opposite. So that's pretty standard for these because you're basically doing the same exact thing as when you set them equal to each other. All right, I'm going to leave the negative inside. You could pull it out if you want, but I'm just going to leave it in. It does not matter for my integration. So getting -1/3 x cubed minus 1/2 x squared plus 6x. And I'm going to evaluate that from -3 to 2. So I have -1/3 times 2 cubed, which is 8, minus 1/2 times 2 squared, which is 4, plus 6 times 2, which is 12. And then when I take off my lower limit, I'm going to be really careful here because remember, I'm subtracting off the whole thing. You might have other ways that you usually do this. I tend to change the sign every time I take off my lower limit, but in this case, I'm just going to distribute. So I have -1/3 times -27 minus 1/2 times +9 minus 18. Making sure I can parentheses match up. Okay, and I'm actually going to rewrite this one more time just for simplicity. Where am I going to put it? All right, so I have -8/3 minus 2 plus 12. Now I'm going to subtract off what happens next. A negative times a negative is a positive, so that gives me 9. So I have -9. And I'm distributing this negative in. So this will be a negative times a negative, which is a positive, 9/2, and then a minus -18, which is plus 18. Pop this into our calculators, and we'll move on. -8/3 minus 2 plus 12 minus 9 plus 9 halves plus 18 is 125 over 6. Please leave this exact. Don't write it as 20.83 or something like that. Leave it exact. This would be the area between the two curves. Okay. One thing I forgot to mention was every once in a while, and I'm going to show you this in the next example, you're going to have, if you're just going to be asked, find the area between the curves, and it's going to be the case where the curves actually intersect more than twice. So here the curves intersect 2 times, 1, 2. So when you found the area between the curves, you just need to find this one area. But you know that they can't possibly intersect again because this is parabola. All it's going to do is go up and come back down. And then h of x is just this linear line. So in this case, you don't need to worry about the fact that, like, for instance, g of x could like come back up and intersect h again, because it's not going to happen. So that's one way that you would know that you only have these 2 intersection points. It's not going to intersect again. You just have one region over which to integrate. Okay, so I really like this particular example because it basically is just a roadmap to helping you solve all of these, because it's got everything that you're going to need in it. You find the intersection points using, by solving basically a system of equations using substitution. You don't need the y values, you just need the x values. You don't have to back substitute. And then you just set up your integral by taking the top function minus the bottom. And if you want to write it out as top minus bottom, that's fine. I know sometimes I hate saying it because I feel like it sounds rudimentary, but even when I go over this with my Calc 2 students, I'm saying top minus bottom. I don't know, it just sticks better for me, and I feel like it sticks better for them. So if you want to use top minus bottom, don't be ashamed. That is essentially what you're doing. Okay, I have one more example for you, and then that will wrap up our discussion on 6-6. I know it's a short one. Do you feel like you've been ripped off? You wanted more out of this? Okay. Let's see. Number 2, find the area bounded by the graphs of y equals x squared and y equals the cube root of x from x equals -1 to x equals 1. Now, this one actually probably seems easier to do when you just read the problem, because the biggest thing here is you're given the x bounds from A to B. So you're already being told, oh, I'm just going from A to B, no big deal. However, there's a little bit more going on with this one. If you were to sketch this, and you can also, of course, put this into your calculator. Okay, so y equals x squared is your parabola. If you want to graph that first, fine. I'm actually going to graph my cube root, graph my cube root function first. So I know, for instance, that the cube root of 0 is 0. And the cube root of 1 is 1. So I know I've got points at 1 and 1. And the cube root of -1 is -1, because remember that I can cube root a negative number as long as it's an odd root. The value inside can be negative. Other than that, I know the cube root of 8 is 2. Oh, I did a terrible job with my axes, but that's okay. You get the general idea. We'll call that -8, and then this will be -2. So when I graph my cube root function, well, that should clearly be down further. But you know what? I know it's in here. My husband organized all my pens and put my whiteout into this little container for me. I know it's the end of the semester. If only this had happened a long time ago, but that's all right. What would I do without my husband? All right, so this is your cube root function. Now the other one is your x squared function. This is your standard parabola. It also goes through the point 1, 1. And it also goes through x equals -1. It happens at y equals +1. So when we graph this, we need to be careful because there's actually a little bit of something happening here. This graph is actually going to go below this purpley graph. I'm going to cut this off for you so you can kind of see what I'm talking about. But remember, we were cutting this off from -1 to 1. And if you don't sketch this out, you're going to have a really hard time seeing this. I'm going to show you in the calculator so you get a little bit more of a close-up view. But essentially, the region over which we're integrating is this one, and then this teeny tiny one. Okay, so this is where we're trying to get the area. Notice that from x equals -1 to x equals 0, the top function is y equals x squared. I'm going to summarize this. From x equals -1 to x equals 0, the top function is y equals x squared. But from x equals 0 to x equals +1, the top function switches. The top function is now the cube root of x. Top function is y equals the cube root of x. So this is one thing you really need to look out for, and this is another reason why it's really important to sketch these, because if we're taking the top minus the bottom, I can't just say, okay, well, I'm just looking for the integral from -1 to 1 of, x squared minus the cube root of x, because that's not going to give me the area, because I need to take top minus bottom, and the top function changes. The top function switches at x equals 0. So that's what's unique about this problem. Now, of course, you could always put this into your graphing calculator if you wanted to do that. If you're kind of like, do I have to do this by hand for all of these? Of course not. Math number 4 gives you a cube root, or you can enter it as x to the 1/3. Okay, so I'm going to zoom standard right now, and then we'll zoom in a little bit so you can see this more closely. All right, so there's your x squared. Here is your cube root. And I think you can see this in this view, that your cube root function kind of goes up. I should have made mine a little bit steeper. But if I go to zoom in, number 2, and then just hit enter, we can get a little bit of a closer view of what happens at 0. Now you can clearly see that change where now all of a sudden your cube root function went from being the bottom function, now it's the top function. All of its y values are above x squared. That's why we need to set up 2 integrals for this. All right, the integral that we're going to set up, or the integrals, I should say, since I already said 2 of them, is that we're going to take an integral from -1 to 0. And this one is going to be when we take top function minus bottom. From -1 to 0, the top function is x squared. The bottom function is the cube root of x. Remember, the cube root is x to the 1/3. And then we're going to add that to the area that we get in the next region. So the area in the next region covers the space from x equals 0 to x equals 1. And then when we're finding the area between these curves, I'm looking at the top minus the bottom. The top function in this case is this purple one, the cube root of x. So this is where we're getting that switch. So it went from x squared minus a third to then switching that x to the 1/3 minus x squared. 1/3, not x to the 1/3, but you know what I mean. And this will cover the whole region. And this uses one of those properties for definite integrals that says we can split up the definite integral at some point and just add it to another interval or integral on the next interval of values. And as long as we make sure to pick back up at the same spot, we're covering that whole area. Another unique thing about this problem, I'm sure you noticed, but when we're finding the area between the curves, we actually really used the intersection point here at x equals 1, where we didn't really need to use the intersection point at x equals -1. So these two graphs actually intersected at 1, and that really matters because let's say they didn't intersect at 1, you would just be guessing. I mean, they could have intersected before this, and you could have had another small region behind it. Like if I had been going up to like x equals 2, well, you'd get this to change again, where the top function would switch over from the cube root to x squared again. So if I had taken this a little bit further out, I would have gotten a whole different region. And that would have been 3 different integrals. So just something to watch out for. If you're not sure, you can always check it by verifying that, I'm going to say verify x equals 1 is an intersection. And you would do that just by setting these equal to each other. So you'd say, okay, well, is x squared equal to x to the 1/3 when x equals 1? Yes, it is. You could, I guess, technically solve for this by taking the square root of both sides. X equals plus or minus the square root of x to the 1/3. I don't know, this is actually kind of messy. You could really just verify that x equals 1 is an intersection. You don't want to end up in this weird situation. This is probably isn't even the best way to do it either. I'd probably say this. Like that. Whoops. Then I would factor this out and then just set it equal to 0. So I'd get, let's see, x, what's 1/3 plus 2 minus 1/3. So x to the 5/3. Of course it is. Remember, when you're multiplying with the same base, you add the exponents. 1/3 plus 5/3 is 6/3, which is 2. And then you would get x to the 5/3 equals 1. And take both sides to the 3/5 power. And you get x equals 1. So it is an intersection. It matters. I know you might be sitting there like, why is she talking about this? Why does this matter? Well, it could matter to you. Not in this problem because I already graphed it out. And you can see from the graph that it's an intersection. You can also verify this in your calculator. You could verify that these two graphs intersect at 1 by going to second trace, which is the calculate menu, and go to intersect, which is number 5. And you could just type in 1. Oh, actually, you can't do that. Sorry. It's a while since I found the intersection point clearly. First curve, fine. Go over to where it appears the intersection is, hit enter again, and it tells you that the intersection occurs at 1, 1. So if you're ever not sure, you're kind of like, I just want to make sure I've got all the regions covered. The intersection does indeed occur at that value for B that you were given in the problem. Okay. So let's just go ahead and find the value of the area here. So this will be 1/3 x cubed minus, increase the power by 1, divide by the new exponents, 3/4 x to the 4/3. And this is going from -1 to 0. And then 3/4 x to the 4/3 minus 1/3 x cubed from 0 to 1. And you can put this in your calculator. Just write a note to me on your test, like I used my calculator to find this value. I'm going to use -1 here. Remember, I'm still subtracting that off. The upper limit gave me 0. The lower limit, I'm using -1. So minus 3/4, and then -1 to the 4/3. Well, -1 to the 4th is +1. Cube root it, and you still get +1. You can put that into your calculator, but you do indeed get +1. And then we'll do the same thing here. 3/4. Actually, this one's a little bit easier to work with. Minus 1/3, and the lower limit zeroes out, so you don't need to worry about it in that case. So we have +1/3, +3/4, +3/4, minus 1/3. This ends up giving you 3/4 plus 3/4, which is 6/4, which is 3/2. Okay. For something like this too, you could, well, actually, I was trying to think of, you could technically use your calculator to verify this, but remember that when your calculator is finding area, it only gives you the area between the x-axis and your curve. So you'd have to do this in a bunch of little parts. So I probably wouldn't use my calculator function here to verify the area. Might be just a lot of work that you don't feel like doing. All right, so that's it for finding area between curves. And this is basically the gist of it. You might need to solve a system of equations to find the bounds for your integral, and that's okay. And you might need to set up a sum of integrals if the top and bottom function switch. That's about as crazy as it's going to get. Okay, so hopefully you will enjoy that. And have a wonderful rest of your day.